Welcome to another one of our lectures in our video lecture series on design of reinforced concrete structures. We completed chapter 3 in our previous lecture, and at the end of the chapter 3 we discussed the analysis of flanged beams. Today we will have a tutorial lecture, and in this tutorial lecture we will do a numerical. In today's numerical we will first deal with the numerical regarding the analysis of flanged beam. So these are the analysis type of problems that we will be dealing now. In the analysis type of problems, you have to determine the moment of resistance of the given T-beam using all the data that you can see in the given two figures here. You have to assume that the concrete that we are using will be of grade M20 and the steel will be of grade Fe415. So you have to calculate moment of resistance of two beams here. These two beams are shown as figure A and figure B here. All the analysis data of figure A and figure B are the same except the percentage of steel reinforcement. The area of steel reinforcement in figure A, we have used 425 mm dia bars, which equals a total area of 1963 mm square. Whereas in figure B, you can see a total of 2591 mm square of steel reinforcement have been used. The other data are the same. We have the width of flange equal to 1000 mm in both cases, the depth of the flange 100 mm, the total depth of the web, that is 350 plus 50, we get 400 mm, the effective cover 50 mm, and the width of our web, which is 300 mm. So all the analysis data are the same except the area of tensile steel reinforcement. We will first determine the moment of resistance of the T-beam shown in figure A. This is the simplest case, and then we will go to determining the moment of resistance for the T-beam given in figure B. So if you remember what we discussed during our last lecture, let me revise a little. We discussed 4 different cases for the analysis of flanged beams. The first case is in which the neutral axis lies within the flange of the T-beam. The second case we discussed where the neutral axis lies in the web and our beam was balanced. The third section we discussed when the neutral axis again lies in the web and our beam is under reinforced. And the fourth section we dealt with in which the neutral axis lies in the web and our beam is over reinforced. In these two cases, when the neutral axis lied in the web, there were further 2 sub cases for each of these cases. If you do not remember that, you can revisit our previous lecture. But for now, let us start with the numerical solution to this numerical problem. So you can see that the first step in these numericals is to determine the depth of neutral axis from the top portion of this T-beam, from this portion here. Since determining the depth of neutral axis will let us know where the neutral axis lies, either in the flange or in the web. So our first step will be the same here. Our step 1 will be to determine the depth of the neutral axis, that is xu. To determine the value of xu, let us assume that what we will assume is, let us assume xu is in the flange. So we will first assume that xu is in the flange and check whether our assumption is correct or not. That means let us say somewhere along this line, this is the depth of our neutral axis xu. So if we assume that the xu is in the flange, we can compare the equation by using this c equals to 2. You can use this equation to determine the depth of neutral axis by comparing the values of compressive and tensile forces. So what is the significance of assuming that the axial lies in the flange in the very first step? If we assume this condition, then as we discussed in our previous lecture, we can treat this T-beam as a rectangular beam of width BW and effective depth D. Since the concrete below the neutral axis will be in tension and can be ignored, we can assume that this T-beam is effectively a rectangular beam of width BF, that is 1000 mm, and effective depth D here. Effective depth is 100 plus 350, that is 450 here. Also remember this. So using this equation, we can determine the value of axial. Axial is given by the formula 0.87 Fy over 0.36 Bf Fck. So 0.87 into 415 into area of steel reinforcement is 1963 over 0.36 into width of our flange is 1000 mm into grade of our concrete is 20. Using this equation, you get the value of axial as 98.44 mm. You can see that the value of axial is less than the depth of our flange, which is 100 mm. So our assumption that the axial lies in the flange is correct here, since the value of axial has come out to be less than df. Now let us find whether our beam is under, over, or parallel section. To do that, we have to find axial max here, which is given as 0.48 D for Fe415 grade of steel. 0.48, the value of D is 450. If you multiply these two, you will get this as 216 mm nearly. Now if you compare axial and axial max, you can see that the value of axial is less than the value of axial max. Hence our beam is under reinforced. So in first step, we determine the axial. Now this is our simplest case. We know the value of axial. We know that it is under reinforced. Now we can directly find the moment of resistance. So in the second step, we are going to find the moment of resistance. Step 2, we will determine mu. And the value of mu is given by the formula 0.87 Fy Ast into D 1 minus Ast Fy Fck Bf into D. That is 0.87 Fy is 415. Ast is given by 1963 and the value of D is 450 into 1 minus 1963 into 450. Fck is 20, Bf is 1000 and D is 450. So this will give you the value of limiting moment of, not limiting, sorry, the value of moment of resistance in Newton millimeter. If you want to convert it into kilonewton meter, just multiply whatever you get by 10 to the power minus 6. Then we will get the moment of resistance of this T-beam is 290.06 kilonewton meter. So this is our answer. This is the value of the moment of resistance of our given T-beam for figure number A. Now let us proceed to the second figure of T-beam. Now let us proceed to figure B. The T-beam has everything same as compared to figure A except the tensile steel reinforcement area, which is 2591 now instead of 1963. So we can see that in our very first step, this changed value of steel reinforcement area will affect the value of axial, which you can see here, has AST in its formula. So let us repeat the same step 1 to determine XU. To determine XU, we will again assume that XU lies in the flange first. And remember, I have told the significance of having this assumption at the very beginning. It will help us to assume that this reinforced concrete T-beam is essentially a rectangular beam of width BF, that is 1000 mm, and effective depth 450 mm. And then only by assuming that XU lies in the flange can you use this formula to compute the value of XU. So let us compute the value of XU now. I'll use the same formula here, 0.87, Fy is 415, and now AST is 2591 over 0.36 into 1000 into 20. This will give us the value of XU as almost 129.93 mm. Now you can see that the value of XU is greater than the value of DF, which is 100 mm. So if you want to draw the depth of neutral axis, your neutral axis now will lie somewhere here. Now this will be the depth of our neutral axis XU. So XU value is greater than DF means neutral axis lies in the wave. Since neutral axis lies in the wave, now we have to find this ratio here. If you remember, DF by D ratio, we have to determine it. The value of DF is 100 and the value of D is 450. So this means it is 0.222 and this value is greater than 0.2. Now since the value of DF by D is greater than 0.2, we have to find a thing called YF, which we discussed also. This YF represents that section of concrete where the strain is at a level of 0.002. And above this level of YF, all of the stress in all of the concrete will be under a constant stress of 0.45 FCK. So let us find YF now. YF is given by the formula 0.15 XU plus 0.65 DF. I think this is the formula that we use for YF. Let me check it. Yes, if you can see here, YF is 0.15 XU plus 0.65 DF, but not greater than DF. Okay, let us continue here. Now it is 0.15 into XU is 129.93 plus 0.65 into 100 here. So let me compute the value of YF here. 0.15 into 129.93 plus 0.65 into 100. So it comes out to be nearly equal to 84.49 mm. Now this value of YF is less than the value of DF, so it's okay. If it had come out to be greater than DF, then we have to use the value of YF as equal to DF. Now you have to use this value of YF to get the actual value of XU here. Remember, the XU that we calculated here, we calculated this XU based on the assumption that the XU lies in the flange. But since we have found here that the neutral axis does not lie in the flange, rather it lies in the wave, we have to determine the actual value of XU. And to determine the actual value of XU, we first determined YF here. Now Comparing the equation of compression and tension, we can determine the value of Fu. So the total compressive force will be 0.36 FCK BW Fu plus 0.45 FCK BF minus BW into YF equals to 0.87 Fy AST. So remember, these two expressions for the compressive forces are the expressions for the concrete below and above the value of YF here. So we got the value of YF to be nearly equal to 84.49 mm here. That means let us say that this is our YF line. YF equals to 84.49 mm. Now what we do in this case is that, if you remember, we divided our T-beam into two parts here. One part is this wave. This is our one part. And then the other part is our this flange portion here. Now above this value of YF here, the flange portion will be under a constant compressive stress of 0.45 FCK. So this expression gives us the compressive force acting on these flanges, whereas this expression gives us the compressive force which is acting on this wave portion here. So now using this equation, determine the value of Fu here. I am just writing the final value here. You just use all the values and then rearrange the equation in terms of Fu. We get the value of Fu to be 169.398 mm. Now we know that this depth of neutral axis, we computed Fu max here in our first case also. The value of Fu max was 216 mm. Now we got this value of Fu to be less than the Fu max. Hence we can say that our T-beam is under reinforced. That means we got to this step here, the third step, or the third case that we discussed in our previous lecture. Remember that in these third cases we had two cases. One case was when the value of df by d was either less than or equal to 0.43, sorry, not df by d, df by xu, and another case was where df by xu is greater than 0.43. So let us find the value of df by xu now. df by xu, df we got is 100 mm as shown in the figure, and xu we calculated here is 169.398 mm, and the value of df by xu comes out to be 0.59. So this 0.59 is greater than 0.43. Now we have to use this case when df by xu is greater than 0.43. To determine the moment of resistance now, we have to calculate the value of YF again. And the value of YF is now given as 0.15 XU plus 0.65 DF. Here, instead of XU, do not use this initial value of 129.93. Now we have to use the actual calculated value, which is 169.398. So 0.15 into 169.398 plus 0.65 into 100 gives us the value of YF is 90.409 mm. Now after calculating this YF, you can calculate the value of FU, MU, that is the moment of resistance, which is given by the formula 0.36 into XU by D 1 minus 0.42 XU by D FCK BW. d square plus 0.45 fck bf minus bw yf into d minus yf by 2. This was the formula that we also discussed in our last lecture for this case here. So we know all the values now. xu is 169.398, d we know already, bw is 300 mm is given in the figure, d is 450 mm, and then bf is 1000 mm, and yf we have to use the calculated value here, 90.409 mm. So substitute all these values into this equation, you get the value of mu to be 369.18 kilonewton meter. So this will be the answer to our problem. So what we did in this video lecture was we determined the moment of resistance of the two T-beams shown in our figure. The T-beams had all the same dimensions except the area of steel reinforcement, which is different for these two sections. So in our first case, the depth of neutral axis lied in the flange of the beam, so it was our simplest case. We just determined the depth of the neutral axis. We found that our T-beam was an under-reinforced beam, and then we used the formula to determine the moment of resistance. In our second case, we found that our neutral axis did not lie in the flange, instead it lies in the wave here. So we first assumed that the neutral axis lies in the flange, and then we determined that depth, but that depth came out to be greater than the depth of our flange, so it was ascertained that the neutral axis lied in the wave instead of the depth here, instead of the flange. So we determined the value of yf, and that yf value we determined and used in this equation c equals to t to find the actual value of the depth of neutral axis here. So you can see the difference here. If it were a simple T-beam in which the neutral axis lied in the flange itself, then this equation was sufficient to calculate the depth of neutral axis. But when the neutral axis lies in the wave, only this equation is not sufficient. We have to determine a value of yf and then use the value of yf in this equation to determine the value of xu. Next, we compared xu with the limiting value or the maximum value of xu and found that our beam was under-reinforced. We went to one of our cases that we discussed in which the neutral axis lied in the wave and was under-reinforced. For this case, we had two sub-cases. The first is when df by xu is less than or equal to 0.43, and the second is when df by xu is greater than 0.43. We determined that this ratio was greater than 0.43. We calculated the required value of yf using the new value of depth of neutral axis, and we used that value of yf in our formula to determine the moment of resistance of our given T-beam. So this is how you solve the problems related with the analysis of flanged beams. In our next lecture, we will again have a numerical class in which we discuss the design of a flanged beam. So we'll meet again soon in that class. Till then, stay safe and thank you.